Hey everybody, and welcome back to Patel Academy. Today I wanted to go over the 2017 AP Physics C Mechanics Free Response questions to give you guys an idea on some of the common types of questions and concepts that could come up on the upcoming AP exam, as well as talk about some of the common errors that students may have faced when they're writing this exam, so that you guys don't face the same errors. Specifically, the AP Physics C Mechanics exam has constantly been transitioning towards more conceptual and sometimes lab-based questions, so I wanted to cover some of those as well as some of the major concepts in terms of the theory, so that you guys are able to understand everything and get really high marks on your exam. Now, I will try and model a timed walkthrough here, but because I will be going on slight tangents to explain some of the concepts, it might go a little bit above the suggested time limit that College Board has. However, just know that when you guys are writing your exams, because you guys won't be doing the explanations, you guys will definitely be able to finish in time. So let's get right into it with question number 1. So we have an Atwood's machine with two blocks of mass M1 and M2 connected by a light string over a frictionless pulley of negligible mass. So question 1A says, on the dots below, I will switch to white for the questions. So it says, on the dots below, which represents the blocks, draw and label the forces that act on the blocks. Each has to be represented by an arrow, and consider the relative lengths. Also in the question, we are given that M2 is always greater than M1. So for these questions, first I'd like to establish my relationship for the forces with respect to each other. So what I know is that the general motion of the blocks is going to be M1 goes upwards, and M2 goes downwards, and thus because of that we know that M1G, so the force of gravity on G, has to be less than the force of tension. Now the force of tension is the same for both block 1 and block 2, and we also have a force of gravity of M2 that is the largest. So when I'm drawing my blocks, I would go something like this is M1G, a little bit bigger is FT, and then even bigger is M2G. So essentially we just need to establish this initial relationship and then draw the forces accordingly. So this first dot represents block of mass M, second one represents block of mass M2. Okay, so fairly straightforward question. Moving on to part B. Using the forces in your diagram above, write an equation applying Newton's second law to each block, and use these two equations to derive the magnitude of the acceleration of the blocks and show that it is given by the equation provided. So for block 1 and then for block 2, we have, we know that Newton's second law says that the net force is equal to mass times acceleration. So I know that the mass times acceleration is m2a, and our net force is going to be the force of tension minus, this is for block 1, so it's m1a. And it's force of tension minus m1g. Similarly, for block 2, m2a is equal to m2g minus ft. And so what we're able to deduce is we can add equation 1 and 2 in order to get acceleration times mass 1 plus mass 2 is equal to m2g minus m1g. So I just added the equations, the ft's will cancel, and then I factored in acceleration. So what we're able to see is that acceleration is equal to, when I factor out a gravity, I get m2 minus m1 times gravity, and then divided by m1 plus m2, which is what we were provided as the equation that we needed to get to. And so that was part B. Fairly straightforward questions. For part C, it says indicate below which quantity should be graphed to yield a straight line slope whose slope could be used to calculate a numerical value for the acceleration due to gravity g. And then we're given a data table to use when we actually do our plot in part D. So what I noticed is that based on the equation that we just found, relating acceleration, this value involving all the masses and gravity, I can rearrange to solve for gravity as being acceleration divided by this entire quantity of mass. And so because we want a straight line with the slope approximately equal to g, we want to relate this to delta y over delta x. And so we can just On our vertical axis, where we're plotting our delta y, or our y values, we just write the analog acceleration. And for our horizontal axes, we want to plot our delta x, and so the denominator of this fraction for g is going to be the quantity m2 minus m1 over m1 plus m2. Now you could have simplified the fraction to bring the m1 plus m2 quantity above, and then plot it that way. So my vertical axis would be m1 plus m2 all times acceleration, and then my horizontal axis would simply be m2 minus m1. That is also a reasonable way, but this one is the simpler one to look at. So you don't have to do any algebraic manipulation, you just take quantity on the top, quantity on the bottom. For part D, we're asked to graph the data points. So first I'll make a table because we're going to need our new data points, and then afterwards I will do the graph. So we have our acceleration, we have our m2 minus m1 over m1 plus m2, and then we have 5 points, so 1, 2, 3, 4, and 5. So our accelerations respectively are 3.02, 1.82, 4.21, 1.15, and 1.71. And then this mass quantity that we have, for the first one, it is 1 over 3. These are just calculations that you can do in your head. They are not challenging calculations. Next one is 7 over 17. Next one is 2 over 14, so 1 over 7. And then the last one is 4 over 24, so 1/6. Now, on the actual AP exam, you would be doing a much more accurate diagram, but because I'm doing it on the side over here, it's not going to be as accurate, but I will state the points that you would get, the nice points that you can use to calculate the slope, as you'll see we do in part E, which you would have noticed if you, on the actual exam, would look a little bit ahead. And so the first step, I think, is we have to define our axes and the units where appropriate. Sorry, that should be seconds squared, not seconds sub 2. In terms of our units, so when you look at our acceleration values, we have a range from 1.15 to 4.21, so basically from 1 to 5. So that's what I'll do. So this will be 0, this will be 1, 2, 3, 4, and 5. And then for this mass quantity, I essentially go, the smallest is 1/7, the largest is 7 over 17. 1/7 is about 0.14, and then 7 over 17 is about 0.41. And so I'll be going basically from, again, 0 to 0.5. 0.1, 0.2, 0.3, 0.4, 0.5. So obviously this isn't as accurate as it could be, but when you actually do your data plotting on the table, it'll be much better. So for this first point, I have 1/3, so about 0.33 and 3.02. So somewhere around here. Next one is 1/5, so 0.2 and 1.82. Something right here. Next one is 7 over 17, so we're 0.41 and 4.21. Next one is 1/7, so 0.14 and 1.15. And then the last one is about 1/6, so 0.167 and 1.71. So 0.16 and 1.71 is somewhere around here. And so we can draw an approximate line of best fit. Now these points are definitely a little bit off scale, like this 0.2 point is probably should be moved up in the actual diagram so that we can get a rough scale. This is approximately what it looks like, and then we can have a plot of a line of best fit as shown here. And so that's essentially a rough sketch of what part D would look like. Now for part E, it says, using a straight line, determine an experimental value for g. So we know that our g is going to be delta y over delta x because it's the slope. So we just have to pick 2 points, x, y, such that we can calculate the slope. And so while it's not fully apparent over here in the picture, there are actually, when you draw it, some really nice points to work with. So the first point was 0.31 and 3, or 0.3 and 3, which you can approximately see over here. So I would write 3 and then 0.31. And then the next one was a little bit down the line. It was about 1 and 0.11 or 0.12. So if I use 0.1, 1 and then 1, then I get 2 over 0.2. Which is 10. And if I decided to do 0.12, so 0.31 minus 0.12, and then 2 divided by that, I get 10.5. So depending on how you interpret it, it could be 0.11 or 0.12. So you would get 10 or 10.5. So I believe anything within that range would suffice depending on how close your points were. You know that this is a reasonable calculation because your estimated value of g, so your actual value of g is 9.8. We're allowed to make the assumption that it's 10. And so something like 10 to 10.5 is reasonable because most of these experiments will overshoot or overestimate the value of g, simply because of some factors that you can't control that are fairly negligible but can affect it. For example, in this case, air resistance. So that was question E. Now for question F, it says, the experiment is now repeated with a modification. We now have an Atwood's machine across a tabletop. So we have M2 hanging off, M1 on the table. And so question F says, for the same values of M1 and M2, when we do both experiments, is the magnitude of tension in the string when the blocks are moving higher, lower, or equal to the magnitude of tension when the blocks are moving in the first experiment? So essentially, is the tension greater in the second experiment or less than in the second experiment or equal compared to the first? So the answer is lower. So in the second experiment, the tension is lower than the first, and I'll go through the mathematical reasoning of why. So in this second system, so originally in experiment 1, our F net was M2G minus M1G. But for experiment number 2, the force of gravity on the first mass doesn't actually affect the acceleration of the system because it's counteracted by the normal force of the table. It's not directly affecting the coordinates of motion, and so it has no play in the actual net force that we care about. And so in this case, it's just M2G minus Ft. That's just for block 2, but overall for this system, it's just M2G. The Ft comes into play when we just consider block 2. But so what this means is that because the total mass is still M1 plus M2, and it's the same values across both the experiments, there's going to be up F net, which means there's going to be up acceleration. Now, when we just consider block 2, for this second experiment, we have F net 2 is equal to M2G minus Ft. So this is the same as the original, except now what we know is that this is M2A is equal to M2G minus Ft. Now M2G is a constant, and we know that our acceleration is increased. So for that to happen, Ft must decrease so that this relationship stays intact. So Newton's second law is still applicable. And so because of that, this is just a proportionality argument. We can say that the force of tension in the second experiment has to be lower or has to decrease to account for this increase in acceleration compared to the first one. So that was question F. Now for part G, it says the value determined for the acceleration due to gravity, g, is lower than in the first experiment. Give one physical factor that could account for this lower value and explain how this factor affected the experiment. So there's basically two main choices. You could talk about air resistance and make an argument, or you could talk about friction on the table and make an argument. It says that there's a smooth horizontal table, but smooth surface does not necessarily mean frictionless. So I'll pick friction just because it's probably the easier one to talk about. So one factor that could account for this lower value is the friction of the table. Why? Because then our F net becomes m2g minus the force of friction of the table acting on 1. And so because of that, our acceleration, we have a lower acceleration. And so because we have a lower acceleration than experiment 1, we would be able to, when we draw a graph, we have lower acceleration, so we have a lower delta y for the same values of delta x. So we have a lower or a smaller slope, and thus a lower value of g. Determined. So it's a fairly simple explanation to give, is that there's an extra force counteracting our force of gravity, and so because of that, our acceleration is going to be lower because there's a lower net force, which means that you're going to have a smaller slope or a less steep slope. So that was question number 1 in full. Now we move on to question number 2. Okay, and it says we have a block of mass m starting on an inclined plane of height h. We slide down the plane, we go onto this horizontal surface, we hit a spring, and it collides with and attaches to an ideal spring. Okay, there's negligible friction between the block and the inclined plane. Spring is negligible mass, so those are all assumptions that we're used to working with. Express all algebraic answers for part A, B, and C in terms of just m, h, and k. And physical constants, obviously. Okay, so A, part I, says derive an expression for the speed of the block just before it collides with the spring. Okay, so the way that I like to do this type of a question is with conservation of energy. It's the easiest way. And so as we know, conservation of energy says that the initial kinetic and the initial potential energy has to equal the final kinetic and the final potential energy. Now, initially, we start at rest, so there is no kinetic energy. At the end, we are on the ground, so there is no potential energy. Now, one of the things is that because we have a spring in play, there is potential energy from gravity and there's potential energy from elasticity. So in this case, because we're working with potential energy from gravity, I like to specify that we're talking about UG has to be equal to KF. Substituting in the formulas, we know mgh has to equal 1/2 mv squared. And solving, we get an equation that you guys are all probably very familiar with. V is equal to root 2gh. So this is something that we've seen a lot of times in a lot of applications involving conservation of energy. So you're honestly very likely to come across this expression. So that was part I. Part 2, or part II, says, is the speed halfway down the incline greater than, less than, or equal to 1/2 the speed at the bottom of the inclined plane? Okay. what we can do here is we can, what's the easiest way? What we know is that from the previous expression, we have velocity is equal to root 2gh, and just using some algebra, which that's equal to root 2 times root h. And so what we know is that velocity is proportional to root h. So velocity divided by root h is a constant. Velocity is directly proportional to root h. And so when we have our h prime is equal to 1/2 of the original h, what we get is our v prime is equal to the square root of 1/2 h, or the square root of h prime, which is equal to the square root of h over root 2. So it's equal to our original v over root 2. So this is essentially a proportionality. Sorry, so I should say that this is equal to, so this is proportional to the original v divided by root 2. And so what essentially we're trying to find over here is that, is the speed halfway down the incline? So is v over root 2, fill in the blank, greater than, less than, or equal to 1/2 v, so v over 2. So this should be a fairly simple blank to fill out. Clearly, this is greater than. So our answer is greater than. Now, what you could have also done was try and do another conservation of energy argument. Now we're halfway down versus fully down, and so you could figure out what the speed is relative to our ending speed. You could set our ending speed to be something like v, and then the speed halfway down the point to be v prime, solve for v prime, but you get the same relationship where essentially your justification for this would be velocity is proportional to the square root of h, and thus when the height decreases by a factor of 1/2, so when we get to 1/2 height, our velocity is essentially decreased by a factor of root 2. So I'll write that. We are decreasing velocity by a factor of root 2, and then we know that root 2 is less than 2, so 1 over root 2 is greater than 1/2. So this is just kind of like the side justification that you could use in your answer. So we know that velocity is proportional to the square root of h. We are decreasing our h by 1/2. We're decreasing our velocity by a factor of root 2. And because root 2 is less than 2, root 2 is about 1.4, so it's less than 2. That means that the reciprocal is the inverse inequality. So 1 over root 2 has to be greater than 1 over 2. So we can verify this as well if you want on a calculator. Root 2 over 2 is about 0.7 versus 0.5. And so we know that our velocity is greater than. Okay, now we're on part B, which says derive an expression for the maximum compression of the spring. So this is where, the thing I was talking about earlier, springs have elastic potential energy. So it's important to separate between gravitational potential energy and elastic potential energy. So what I'll do is, now we can consider solely the block on this horizontal surface. So we can forget about the inclined plane for now. The potential energy, if I write another conservation of energy, I guess, statement, I get K initial plus U initial is equal to K final plus U final. Now, if you consider this from initially, or if you consider it from right when it gets off the ramp, both suffice. I'll show it both ways just in case. So let's say if we start it from the very top, right? So if we paint our scenario or frame of reference as starting from the top of the inclined plane, and the ending point is when it's compressed against the spring. So we start off with no kinetic energy, and we end off with no kinetic energy. So we get U gravitational in this case is equal to U spring. Now the reason why is because at the end there is no gravitational, but there is still elastic potential. The other way that you could go about doing this is you could consider it just after we ended the ramp. So if I write out Ki plus Ui is equal to Kf plus Uf, right after we get off the ramp, we have no gravitational potential energy. Once again, once we're compressing against the spring, we have no kinetic energy. So we get Ki is equal to this U spring. What we saw from earlier, Ki is equal to U gravity, the initial. So you could either directly substitute for Ki, or you could just relate it back to Ug, and you'd still get to this expression, Ug is equal to Us. Now from there, we can substitute our values. So if Ug is equal to Us, we have Mgh is equal to 1/2 Kx squared. This x being our x max value. And so x max is equal to, this might be another one that you've seen before, it's going to be root 2mgh over k. So you guys might have seen this expression as well. It is also fairly common when you're working with springs along with inclined planes. But yeah, we don't have a value for k, so we just have to express our answer in terms of k. So that was part B. And for part C, it says determine an expression for the time from when the block collides with the spring to when the spring reaches its maximum compression. So now we want to solve for the time. So while there are, once again, a few ways of doing this, the easiest way, in my opinion, is to consider it from a simple harmonic motion or SHM perspective. And so what we know is that the time taken is going to be equal to 1/4 times the period. So if you think about the spring when it's compressing to its maximum, length, or when it's reaching its maximum amplitude of compression, that's going to be 1/4 of the total cycle for SHM. So if we draw it, let's say if the spring starts at position 0, we're going to have a compression, then we're going to have restoration, then we're going to have extension, and then we're going to have restoration. So this would be one cycle. And so just this compression is 1/4 of this cycle, or 1/4 of the period. Now the other thing that we know is in regarding simple harmonic motion of a spring, we also know that T is equal to 2 pi root mk. So that's an equation that you guys should know. It's given on the formula sheet as well. And so we can just directly write our time, it can be related as pi over 2 times the square root of m over k. This is probably the easiest way to go about this question. Okay. So just like I said at the very start of the video, a lot of times there's a focus on energy in the second question, but they can often throw in stuff about springs. Usually it's Hooke's law, but sometimes they do throw in small things like simple harmonic motion, just to see if you did actually review that small concept. Okay, so we're now given for part D, the block is again released from rest at the top of the incline, and when it reaches the horizontal surface, it is moving with a speed v0. Now suppose the block experiences a resistive force as it slides on the horizontal surface, and the magnitude of this resistive force is given as a function of v. F is equal to beta times v squared, where beta is a positive constant with units kilograms per meter. So this part 1 says write but do not solve a differential equation for the speed of the block on the horizontal surface as a function of time t before it reaches the spring. Express your answer in terms of m, hk, beta, v, and physical constants as appropriate. Okay, so in this case, the easiest way that you do this, the only way technically, is just writing an F net statement. So that's equal to ma, which is equal to, well, our F net is we have a force going backwards, and then we have our initial velocity. So the only net force that we have is this resistive force that's acting on us because of our initial velocity from our kinetic energy obtained from going down the inclined plane. And so because we have ma is equal to negative beta v squared, we know that acceleration is dv by dt. So you can write m dv by dt is equal to negative beta v squared, or sometimes we like to write it as m v dot. The dot representing the derivative is equal to negative beta v squared. So that's our differential equation. We were told not to solve it for that part, but now it says using the differential equation from part D1, show that the speed of the block v at t as a function of time can be written in the form 1 over v at t is equal to 1 over v naught plus beta times time over mass. And v naught is the speed at time t equals 0, so it's the initial speed once it reaches the horizontal surface. Okay, so in this case, we're essentially asked to solve. And so what we get is rearranging. Keep in mind when we're solving these differential equations, we want to separate our variables and then integrate both sides. So what I get is on one side, I'm going to bring over the 1 over v squared. So I'm going to get 1 over v squared dv is equal to negative beta over m dt. This is just a simple separation of variables. I'm going to now integrate both sides. Now in this case, it might be a little bit easier for me if I don't integrate with bounds because I'm given an initial condition, so I don't need to worry necessarily about integrating with bounds properly, because when I integrate and I get my constant, I can simply replace that with my v naught or the corresponding expression. And so the integral of 1 over v squared becomes negative 1 over v. And then I get is equal to, this becomes negative b over m at time t plus c. And so based on that, well, I know that I'm going to be, at time t equals 0, I'm going to get negative 1 over v is equal to c. Now, negative 1 over, at time t is equal to 0, I get negative 1 over v is equal to c, or c is equal to 1 over v. Now at time t equals 0, my v is v naught. And so I know that my c is 1 over v naught. So because of that, so I write it a little bit neater to the side. Time t is equal to 0, v is equal to v naught. I get the expression negative 1 over v naught is equal to c, so c is equal to 1 over v naught. So then I get my negative 1 over v as a function of time. I should probably have specified that here. Is equal to negative b over mt. And then, sorry, this would be negative 1 over v naught, not positive. Negative 1 over v naught. And so we get negative 1 over v naught. And thus I can solve by saying 1 over v at t, just by flipping the signs and everything, is equal to 1 over v naught plus beta times t over m. So it's just the differential equation. We utilize our constant of integration. Now, if you did want to integrate by limits, in this case, you could. You could integrate the left side, so the 1 over v squared side, between 0 and v at t, because we're essentially progressing our function from v is equal to 0 all the way up to v is equal to v at t. And then the right side, our time goes from 0 to t. So if you did that, you could also solve for the corresponding proper equation. Okay, so that shows how we can derive this expression from the differential equation. Now part E, a little bit of a graphing exercise. Luckily in this one we don't need to be super precise, so this is my x at t, this is my v at t, and down here I'll do my a at t. So it says sketch graphs of position x, velocity v, and acceleration a as a function of time as it is moving on the horizontal surface before it reaches the spring. Okay, so the easiest one in my opinion, to consider is v at t first, and then we can interpret the other ones correspondingly. And so, or even, what's easier, v at t or a at t? Both of them are fairly simple, but I can start with v at t. And so what we know is that the inverse of v at t, so 1 over v at t, sorry, is equal to 1 over v naught, so it's a constant, plus beta times t over m. And so because this is a reciprocal, we can take the reciprocal of both sides. So I'll do this on this next slide. So we have 1 over v at t is equal to 1 over v naught plus bt over m. So my v at t is equal to 1 over 1 plus v naught bt over m, which is equal to m v naught over m plus v naught bt. And so we get this expression for v at t. And so what we notice is that we start off at a velocity v naught, and then as t increases, our velocity function will decrease. And so we get an approximate model like so, where we start at our velocity and the velocity drastically increases and approaches a value because of the resistive force that changes as a function of velocity. So you could do this mathematically and get the relationship, or you could just think about it conceptually as to how exactly the velocity function would change. So we have a resistive force proportional to v squared, and so we're guaranteed going to get an inverse relationship. So back over here, we start at our velocity v naught, and then we have a transition like so. And so we have this graph. Now our position is fairly easy to interpret from over here. We start at position 0, and then we grow gradually, but then our change in position decreases until we would eventually level off. So we get something like this. And then, for this velocity graph, I'll specify that I intersect because it's a little bit harder to see. Oops, it does not go over 0. Something like that. And then I can go upwards like that. So it does intersect at time t equals 0, we have v naught. And then the acceleration is similar, except that you have to consider that we start negative and then we approach 0. So it would be something like this. So the key aspects of this graph are that the displacement curve is concave down and we approach a horizontal asymptote, velocity is concave up and we approach 0, and then the acceleration is concave down but we approach 0 as well. Okay, so that was part E. Now if you guys would like further explanations, I would highly suggest that you guys consider reviewing kinematics for nonlinear motion, because it's those cases where you have these special graphs involving a change in concavity and horizontal axes compared to your regular linear graphing, or maybe your regular quadratic graphing. So I highly recommend you guys review those. Okay, so we're on to question number 3 now. So a uniform solid cylinder of mass m is equal to 0.5 kilograms and radius 0.1 meters is released from rest. It rolls without slipping down a 1 meter long inclined plane, and it is launched horizontally from a horizontal table of height 0.75 meters. The inclined plane makes an angle of 30 degrees with the horizontal, and the cylinder lands on the floor a distance d away from the edge of the table as shown in the figure above. There is a smooth transition from the inclined plane to the horizontal table, okay, and the motion occurs with no frictional energy losses. The rotational inertia of a cylinder around its center is mr squared over 2. Now that's one that I personally think that you guys should know. In this case they give it to us, but I don't know if they always give it to us, so I would recommend knowing the important ones like the rotational inertia of a sphere and of a cylinder. Okay, so part A says calculate the total kinetic energy of the cylinder as it reaches the horizontal table. Okay, so in this case, the total kinetic energy, we don't necessarily have to consider rotational and translational in this case. The reason why being that the total kinetic energy, which would just be the sum, can simply be derived from a conservation of energy argument as we would do with a normal block going down an inclined plane. We don't necessarily need to consider the rotational and translational analogs respectively. So I can just say my K initial plus U initial is equal to K final plus U final. At the start, sorry, I was just reading the question to figure out how we get the height. So at the start we have no kinetic, at the end we have no potential. And so we know that the U of gravity along the top, keep in mind I still like to specify U of gravity is equal to the kinetic energy as the cylinder reaches the table. Sorry, this kind of makes it seem like it's the kinetic energy of the table. It's the kinetic energy of the cylinder at table. And so we have our K total, or the K of the cylinder at the table, is equal to mgh. Now we know that our mass is 0.5. We know that our gravity, I'm going to use 10. You can choose to use 9.8. That's up to you. And then our height, well, we're given that the inclined plane is 1 meter long, and we're given that it's at a 30-degree angle, so the height is just 10 sine. So, or sorry, 1 times sine of 30. And so what we get is sine of 30 is 1/2. So I essentially get 10 over 10 times 1/2 times 1/2, or 10 over 4, which is 2.5, and it's joules. So our total kinetic energy is going to be 2.5 joules. Now for part B. It says calculate the angular velocity of the cylinder around its axis at the moment it reaches the floor. So this is where we would need to consider the rotational and the translational analog in order to consider angular velocity versus regular velocity. So we know that our K total is equal to K translational plus K rotational, which is equal to 1/2 mv squared plus 1/2 I omega squared. So we know that. I'm just going to switch to the next slide. So 1/2 mv squared plus 1/2 I omega squared is equal to K total. Now what else do we know? Well, because we're rolling without slipping, so we know that our velocity is equal to our radius times omega. So I can resubstitute in here by saying that K total, sorry, I switched sides again, is equal to 1/2 mass R omega squared plus 1/2. Now our inertia we're given is mr squared over 2 times omega squared. And so what I can do is I can simplify this. This becomes 1/2 m r omega squared still. This one becomes 1/4 m. Oh, sorry, this mass is capital M. It's just the mass of the object. So this becomes 1/4 m, and then because we have r squared omega squared, I can rewrite this as r omega squared. So we can now combine these together. So it would become 3/4 m r omega all squared. And so my omega is now going to be, I can simplify this as 3/4 m r squared omega squared to make it easier. And so my omega is going to be the square root of 4/3 times K total divided by mr squared. And so I can plug the values in. So my K total is the 2.5 joules that I found earlier. So I get 2.5 times 4, which is 10. Now on the bottom, I have 0.5 times 0.1 squared, and then times 3. So I have 10 divided by that answer, and then we take the square root. And so we should get something like 25.8, I believe. Let me just do this one more time. So it's 4 times 2.5 divided by 3 times 0.5 times 0.1 squared, and then square root. So yeah, we get 25.81, or 82 I should say. 25.82. And so I believe if you use 9.8 initially for gravity and kept that answer, you get something like 25.6. Otherwise, it's acceptable to go anywhere up to 26 radians per second. So our units would be radians per second. So yeah, that was the angular velocity. Now we go to part C. This was an interesting question because it seems very simple. It says calculate the ratio of the rotational kinetic energy to the total kinetic energy for the cylinder at the moment it reaches the floor. So we're essentially trying to find K rotational over K total. Now what we know is that our K rotational is 1/2 I omega squared. Our K total, it's interesting because you have to consider what some of the people forgot to do is they simply put 1/2 mv squared plus 1/2 I omega squared, but you also have to account for mgh as well. So at the moment it reaches the floor, we have 1/2 I omega squared plus 1/2 mv squared plus, now you also have to consider the the kinetic energy accumulated from dropping down from the table. So the height of the table, so at the start of the table, I'll just draw this here, we have mgh, h being the height, and so it all gets converted into kinetic energy. So kf is equal to ug, which is equal to mgh. And so a lot of times people either misread the question by saying we're still on the table instead of on the floor, or they forgot to just account for this extra potential energy in general. So we have plus mgh, that coming from conservation of energy from transitioning between the table and the floor. Okay, now we have, once again, 1/2. We know that this is mr squared over 2 times our angular velocity squared over, same thing, 1/2 times mr squared over 2 times the angular velocity squared plus 1/2 m, this is r omega squared again, this is going to be mg, and then times the height of the table. And so we can rewrite this. We get, from the last part, I know that the bottom 1/2 I omega squared plus 1/2 mv squared will simplify to 3/4 mr squared omega squared, and this top will be 1/4 mr squared omega squared. So we're left with r squared omega squared over 3 r squared omega squared, and then plus 4gh table. So this is just a matter of plugging in values to solve. And so afterwards, we can just sub in our corresponding values. So we know that our radius is 0.1. We know that our mass is 0.5. Our angular velocity we derived was 25.8. It can be 25.6 or 26. whichever one you choose, divided by 3 times those values. Our gravity we can use as 10 again, and our height is 0.75. And so plugging that in, we get times 25.8 squared divided by 3 times 1 squared plus 4 times 10 times 0.75. So I get 0.133. And this ratio would be joules over joules, so the ratio has no units. And so the accepted range, I believe, was something like 0.133 or 0.132 to 0.135. So anything within that range would be acceptable. So this was just working through the corresponding values in order to figure out the ratio. So I did a little bit of it within this second and then this third step. I did a lot of algebra just directly. So if you don't know how we got some of these values, like the 4, just consider that we have 3/4. We have 1/4 on the top, 3/4 on the bottom. So I just multiplied and canceled out the corresponding values, and that's where we're left with 3r squared omega squared, and then that's where the 4 comes into play. Alright, so for part D, it says calculate the horizontal distance d. So it's a fairly simple question that we've got over here. So for part D, essentially what we need to do is we need to utilize kinematics first in order to figure out the time that it takes for you to travel this distance. Now this is just a normal kinematics setup where we have an initial horizontal velocity, no initial vertical velocity, and we just have to find the distance traveled. So first of all, I'll use this formula, y minus y0 is equal to v naught t plus 1/2 at squared. Our v naught t, well, we have no initial vertical velocity, so it goes to 0. And then our delta y, so y minus y naught, our delta y is negative 0.75, which is equal to negative 1/2 gt squared. So our t is essentially equal to the square root of 1.5 over g, or 1.5 over 10, which we get to be 0.387. Okay, so we have our value of t, 0.387 seconds, or 0.39 seconds, depending on how you round. And then what we can do is we can say that the change in x, as we do in normal projectile motion, is equal to our v naught with respect to x at t. Now what we also know is that, so we're trying to find essentially this delta x, which is equal to d. And what we also know is that because initially our cylinder had a smooth transition from the inclined plane onto the table, it's still rolling without slipping. And so because of that, we can still say that this is r omega t. And so what we can say is that this is equal to 0.10 times our angular speed, which is 25.8, I believe, if I remember correctly, and then times our time, 0.387. And so plugging that in, it is 0.1 times 25.8 times 0.387, which is equal to 0.998, which is approximately 1 meter. So we can make that rounding, and so we essentially get a very simple answer of 1 meter. Okay, so part E is where students sometimes got a little bit messed up, because this is where you get the conceptual questions regarding rotational motion, which are often some of the hardest questions. So now we're doing an experiment with a sphere of the same mass and radius, but the rotational inertia is now 2/5 mr squared. So is the total kinetic energy of the sphere at the moment it reaches the floor greater than, less than, or equal to the total kinetic energy of the cylinder at the moment it reaches the floor? So the total kinetic energy of the sphere when it reaches the floor, we have to consider is that it still follows the same distance. It follows from the same height as the cylinder, they have the same mass, So the sphere-Earth system has the same initial potential energy, and it all gets converted into kinetic energy, so it's equal to. Why? Because same mass, and same height, same initial gravitational potential energy. And so because it's the same initial gravitational potential energy, it all gets converted to kinetic energy. So it's the same for both at the end. Okay, so that was part one. Part two says, is the rotational kinetic energy of the sphere at the moment it reaches the floor greater than, less than, or equal to the rotational kinetic energy of the cylinder at the moment it reaches the floor? So now we're just considering rotational. And so the answer, if you think about it, the rotational inertia of the sphere is 2/5 mr squared versus mr squared over 2. So 1/2 versus 2/5. The rotational inertia of the sphere is less than the rotational inertia of the cylinder. So because of that, the sphere will rotate faster. So if you think about what inertia actually means, it's the resistance towards movement, towards sudden movement. And so because there's less rotational inertia, the sphere will rotate faster. So with more rotations, there's a greater linear speed, same mass, increased linear speed, increased kinetic energy. And so because the total is the same, the total kinetic energy is the same, and then there's an increase in linear kinetic energy, there's going to be a decrease in kinetic energy. So I'll just write that all out, but I thought I'd just explain my thoughts at first. So what do we have? The inertia of the sphere is equal to 2/5 mr squared versus the rotational inertia of the cylinder, which is 1/2 mr squared. So the rotational inertia, this is 0.4 versus 0.5. So IS is less than IC. So lower inertia equals up rotation by the definition of inertia. We also know that V is equal to R omega because we're rolling without slipping. So up rotations equals up angular speed, which is equal to up linear speed. Now we know that our K total is equal to our K translational plus K rotational. Now we can argue that the ratio between the rotationals of the two, the easiest way is that the K total is going to be the same. Now the rate at which the linear speed increases means that the translational kinetic energy is going to increase much faster. And so because of that, this is going to be smaller to account. Sorry, I should write this as a constant. For a constant total kinetic energy. Now, of course, you could argue something like, oh, well, the rotational kinetic energy is also affected by the increase in the number of rotations, but, I should probably also specify. Here, mass is constant. So, going back to what I was saying, because some students would say, oh, it's equal to, because while the translational is increased based on this relationship, the rotational kinetic energy would also be increased, but you have to consider the ratio or the rate at which it's changing, and so overall the rotational kinetic energy of the sphere would have to be less than the rotational kinetic energy of the cylinder, because the rate at which the translational kinetic energy is increasing at the moment it reaches the floor is significantly larger than its change in rotational kinetic energy. So you essentially only have to consider the change in the translational as it's going through that projectile motion and reaching the floor. So that was part 2. Now we're on part 3. And so it says, is the horizontal distance the sphere travels from the table to where it hits the floor greater than, less than, or equal to the horizontal distance the cylinder travels from the table to where it hits the floor? So this one is essentially playing off of part 2. We know that this is going to be greater than. We've already established that there's going to be an increase in the linear speed v. And so because of that, there's going to be up initial velocity, and thus up distance traveled horizontally. So we can basically see that with the kinematics equation, x minus x0 is equal to v naught at t. If we increase our v naught, then the distance delta x, or x minus x0, is obviously going to increase. Okay, so that was part 3. So that marks the end of the AP Physics C Mechanics 2017 free response questions. I'd say the hardest one on this was honestly the E part 2, the rotational kinetic energy at the moment of reaching the floor, whether that was greater than, less than, or equal to, because it involved a little bit more conceptual thinking than usual in terms of the relationship between not only linear and angular velocity, but also between total kinetic energy and its parts for the translational and rotational analogs. So other than that though, I think this was a good exam because it tested a wide range of things from differential equations, all the rotational stuff. It had a lab component in as well in terms of like sources of error. So a very fair and a very in-depth while also broad test paper. I hope you guys all enjoyed this video going through the questions and solving them. Of course, if you have any confusions about anything, feel free to leave a comment down below. I'll be glad to answer them. Like the video if you learned anything from it. I really appreciate all your guys' support. It's really motivating, especially during this time, right before AP, that you guys are showing this much support. Like, comment, and subscribe. Hit that notification bell for future videos. And I hope to see you guys next time on another Patel Academy video.